Welcome back to Learning with Ms. H. Today we're going to talk about the life cycle of a star. The title of the lesson is Formation of Stars. You'll need something to write with right on, and you'll need to go ahead and pause me and do the bell work. So in your notebooks, answer the problem, what causes tides? Go ahead and pause me and come back. All right, now that you've done that, let's come down here and take a look at the homework really quickly. So those of you that don't want to go through notes with me can go ahead and move on. So in the homework, we have the formation of the stars homework, and basically what it is ordering. So you have two questions here. In the notes, we'll learn about two paths that the life cycle of a star can take. So path A is on top, path B on bottom, and you're just going to take these and drag and drop them wherever they need to go to put them in the correct order. Use your notes and you should have no problem with this. It is for points, so please make sure you get it done. So let's go ahead and jump in to notes on star formation, formation of stars. This first image is a summary of all of the notes put together in one visual form. Go ahead and copy this down into your notebooks. Pause me, come back when you're done. In between nebula and main sequence star, you're going to add the protostar in, P-R-O-T-O-S-T-A-R. So just put a little circle in here in between that says protostar, and then come back once you've finished. All right, welcome back. So we're going to start off with talking about what a star is. It's basically a glowing ball of plasma. There's nuclear fusion happening in the middle of this. So remember that plasma is a state of matter. It's not really a solid, not really a liquid. It's kind of a thick, gooey kind of thing. Nuclear fusion is a vocabulary term. That's when you have two hydrogen atoms that have one proton and one electron that combine together and they fuse or join together, which means they have two protons and two electrons, turning them into a helium atom. Hydrogen and helium are the most common elements in a star. The main characteristic of a star is that it's going to give off huge amounts of energy as heat and light, and the light can be anywhere in the electromagnetic spectrum. Remember, when you go through notes, you can always pause the video and then pick back up once you finish your slide. So let's take a look at this life cycle. Baby stars are always going to start off, they're going to be born in a nebula. A nebula is basically a cloud of dust and gas hanging out in space in the same vicinity. It can be any shape. We've got a couple different shapes here. You've got one that's a cloud that kind of has a boomerang opening in the middle. This one's kind of all over the place. This one makes pillars. All of these are considered nebulae. That's the plural of nebula. Step 2 is going to be the protostar, and it's a dense region of gas that's really compact, and it's got gravity sucking things into the middle of it, and it's eventually going to form a sphere and keep pulling matter in until it gets hot enough to start nuclear fusion and become a star. So you have gas here, and then you have this really dense area in the middle that's pulling everything in and heating up. Step 3 is to become a new star. So once we reach 10 million degrees Celsius, nuclear fusion is going to begin, and those hydrogens are going to join together to make heliums. This is when it is officially named a star. Stars go into what we call the main sequence. They become main sequence stars. We're going to be talking about an HR diagram in our next lesson, which is basically a way to plot stars based on their temperature. And you'll see what I mean with main sequence in a visual representation when we get to that lesson. But basically, a main sequence star is any star that is currently fusing hydrogen to form helium. This releases huge amounts of energy when it does this, and that's what produces our heat and our light. Generally, stars will stay in the main sequence for about 10 billion years. That's how long it takes to consume all the hydrogen and turn it into helium. There can be other elements in the core, and the appearance of the stars is based on how much of those other elements and what other elements are there. We call those trace elements. Most of the star is made up of hydrogen and helium. A star is basically going to be in a balancing act. The core is where we generate heat, and then that radiative and conductive zones outside the core here are what move energy around inside the star. It's going to try and move the energy from the core to the outside and maintain what's called a hydrostatic equilibrium. Equilibrium means everything is happy and equal, and there's no, it's not, one side's not bigger than the other or has more matter than the other or anything. Everything's all equal throughout. The problem with stars is because of the incredible weight of all that mass being pulled in towards the core, gravity's pulling all of that in, trying to collapse all of the gases in on the core. So that's why we need that nuclear fusion to happen and push the energy back out so it balances out the gravity pulling in. If nuclear fusion stops, you have an unbalanced star. Unbalanced stars are not happy. Internal forces are no longer happening. We don't have that nuclear fusion, so they're no longer pushing out. So what happens is all of those gases collapse in on the core. Once all that hydrogen gets consumed, we suddenly have a collapse of the star. When a star collapses, it's going to release huge amounts of energy, and there's two paths that it can take from this point. If it's a smaller star, so something around the size of the sun, maybe a little bit larger, all the way down to anything smaller than the sun, it's going to take path number 1 for the smaller stars, and it's going to become a red giant. If it is about 3 times the mass of the sun or more, it's going to take path 2 for larger stars and become a supergiant. So path 1, this is the same image that you copied down before, so you don't have to write it down again. But this is the bottom part of that summary slide. So path number 1, red giants. You have a collapsing star because of that lack of nuclear fusion. So everything collapses in, the core starts heating up, and now all of a sudden the core has gotten hotter. So now the core is hot enough that it can fuse helium into carbon. Once that fusion starts again, you're going to regain balance in the star. You're going to have more energy pushing out. You're going to start losing some of those outer layer of gases. It's going to get huge. As it's pushing everything out away from the core, it gets larger and larger. And these red giants are going to last for about 100 million years. On the right-hand side here, you have a sketch. This is not an image. This is a sketch of approximate proportions of what it would look like if you lined up our sun. This little pinpoint is the Earth, and then this giant big red semicircle is a red giant. And this part of the red giant is basically equivalent to this part of the sun. So they're huge. Step 2 in path 1 is actually step 5 overall, and that is becoming a white dwarf. Now, a white dwarf, all the carbon has fused together. There's no more carbon left to fuse. We're unhappy again because we have no internal forces happening. The core is super, super dense because it's got all that carbon in there. It's very, very hot. If you were to take a tablespoon of the core material and bring it back to Earth, that 1 tablespoon would weigh 5 tons. So equal to a couple cars for 1 tablespoon of it. Super dense. White dwarfs are about 8,000 miles in diameter, and it takes about 35,000 years for them to start cooling off. Once they do, their light becomes less and less, and they will eventually lose all of their light. And that leftover light after that 35,000 years is due to leftover residual heat. Over here on the right, we've got a picture of an area of space, and then we've got a close-up of it, and we've circled the white dwarf stars in the image. They're basically little pinpoints of white. Step 6 is a black dwarf. So once the white dwarf cools, it's going to go through the visible spectrum, changing colors as it goes, and eventually it's going to turn into a black spot that we really can't see because there's no light from it at all. It will continue to have gravity and put off low energy transmissions, so things like radio waves. So we know it's there. We can still find it by looking for those radio waves, but we can no longer see it because there's no visible light. Second path we can take is to go up through supergiants, and then it's going to split off here at the end again to two different outcomes. So a red supergiant is going to expand even larger than the red giants. It's going to be anywhere from 10 to 1,000 times larger than our sun. If you were to plop a red supergiant down on top of our sun, it would extend out past the orbit of Uranus. So it would take up most of our solar system. An example of a red supergiant is the star Betelgeuse from the constellation Orion here. It has a little bit of an orange hue to it, and we've got some brackets here that show you the size of the star in comparison to Earth's orbit and Jupiter's orbit. So it is massive. Step 5 for the red supergiant is it's going to die off and become a supernova. Once it's fused all of its carbon, it goes through the process of fusing the hydrogen, fusing the helium into carbon, then it fuses carbon into iron. Once it's done that core is all iron. There's no more fuel left to consume. It's completely done. There's nothing else it can do. It's going to collapse in on itself in less than a second. So once it's done, it just collapses. It causes a huge explosion that we call a supernova. The supernova is going to send a shock wave out into space that's going to blow all of that dust and debris, all of those outer layers of the star are going to all get blown out in all directions. It's super bright. It happens very quickly in an instant, but the light from a supernova can be seen for years, and it's brighter than other galaxies. There's a couple of things that can happen with a supernova. If there's nothing left, you just have empty space, all is well, and there's nothing else that's going to happen from there. You end with the supernova and then get empty space. If there is anything of the core left, there's two things that can happen. These are some images of some supernovae happening. So those are star explosions right there. And then this is the aftermath here, all the layers getting blown out away. So two things can happen if you have core left. The first is it can become a neutron star. It's basically a dead star. You've got the core there, but it's less than 3 solar masses. The solar mass is the mass of our sun. So if it's less than 3 solar masses, it's really, really small, and it becomes a neutron star. It sits there, nothing really happens. It just exists. If it is larger than that, though, it can become a black hole. Black holes cause problems because they have so much gravity that they suck in everything around it, including light. Nothing escapes a black hole. It all just spirals down towards the center of it, towards that core, and gets sucked into it. This is the life cycle of a star. Once you're done with this, there's one more image here, and this is basically walking you through the process of what can happen, some of the things that can end up where the star starts and finishes. So it's just kind of a cool little diagram of it. Once you're done with these notes, you've caught up with everything. Go ahead and go do your homework assignment where you are ordering all of the steps in the life cycle of a star. You can watch this video as many times as you need to go back, fill in any notes you need to, and we will see you next time.